That.
Okay, so welcome everybody to the final session of this meeting. It's a pleasure and an honor to have Professor Demetrios Papageorgiou from the Department of Mathematics at Imperial College London as our plenary speaker today. Professor Papageorgiou holds a chair in applied mathematics and mathematical physics at Imperial. He is, of course, well known in the community and needs no introduction. Briefly, his research interests are broad, including nonlinear waves, fluid dynamics, in particular modeling different physical effects such as surface tension, electromagnetic fields, etc., in interfacial flows. He's also interested in the application of these ideas in micro and nanofluidics. Today, he'll be talking about waves on the microscale, order, chaos, and its control. Demetrius?
Thank you very, very much. It's a great pleasure to be part of this first conference that you guys are organizing. So best of luck with it, and we look forward to many more. So I will give you kind of an overview of a lot of things. I thought that would be better rather than just concentrating on one problem. And before I do anything, let me first of all dedicate this to the early career people that I've been very fortunate to work with. And there's a lot more than the 6 you see here. But these ones are selected because they've been involved in the work, or they've done most of the work that I will present. So Susanna, you know, Anna is in Nottingham, Alice is in Manchester, Radu in Warwick, Ruben is still here at Imperial. I was looking for a picture of Paul. I couldn't find one, so I put one up. That's one of his favorite pastimes nowadays, riding bikes. So he's there in a kind of an unstable equilibrium point. So, okay, so let me continue with the motivation. So the motivation really is to see what we can do in situations where we don't have gravity or any large external forces like we would see in the ocean, or strong winds or things like that that cause large scale energetic motions. And we're instead on the microscale, or kind of millimeter or below type of scale. So the device sizes get very small. So you have to think of different ways of affecting the flow, how to impose instabilities, enhance mixing, and so forth. So what happens there is that, especially if you have fluids that do not mix, oil, water, as it's very, very normal in these types of applications, what you have is large surface to volume ratios. So interfacial effects become important. So things like viscosity, surface tension, electrical charges, temperature, all of these things become important. So, so here's really the idea, right? So suppose here are 2 flows that would happily sit there forever unless they evaporate. So that's a drop on a substrate. Happily, it will sit there. Or a liquid layer just sitting on a substrate. So the question is, at these very tiny scales, what can we do to generate motion? And of course, we saw last week, the ones of you who saw the talk by John Bush, the way they generate flows is by moving this substrate up and down and generating these waves at the interface. So here are the types of external effects we can impose. Temperature variations will change surface tension and therefore cause flow. Substrate inclination oscillation, we mentioned that. The ones in red are the things I'm going to mostly concentrate on. And one is blowing and suction through the substrate. And we're going to use that for control purposes, as we'll see later on. But perhaps the most dramatic way of affecting these flows is with electric and magnetic fields. And I will begin by showing some applications there. So we can produce controllable motions without any moving parts. That's kind of the idea, because it's difficult on the microscale to produce, to introduce moving parts. Electrohydrodynamics goes back a long, long time, but I will start from the 1960s and some seminal work by G.I. Taylor, where they did some experiments as well as theory, where they showed that if you take a liquid that's conducting, and then this region is air, and you put an electrode above it, so there's a potential difference, an electric potential difference between the electrode and the surface of the fluid, then you can get these bumps, these motions. And in fact, they very ingeniously, they came up with steady state type solutions that they then thought about how to analyze with bifurcations and so forth, the instabilities and so forth. So this generated a lot of interest. And if we wind forward about 35 years or so, this was applied on the microscale. So these are some experiments which are called lithographically induced self-assembly and self-construction. And in fact, I'll show you some simulations in a minute. So the idea here is you've got this liquid on a polymer or something, and you want to make electronic components. So you want to build motherboards with tiny wires and so forth. Well, the idea is if you can self-organize this liquid into columns like this, and then you reduce the temperature, and then they solidify, then peel off the top layer, you end up with a circuit. That's really the idea. So under normal conditions, under its own instability conditions, the liquid will go unstable and form these structures, but you can also coax it into reproducing a mask that you put on top of it as an electrode, just by playing with the intensity of the electric field locally. So let me show you, let me show you how this is done. Here's some simulations that Radu did. So there are two cases. One will have no topography. The other one will have topography. So let me put them side by side and we can see them. So this doesn't have topography on the top and this one does. And the electric field is switched on and we can watch the waves form. So we see that in the bottom case, it likes to go and meet the protrusions because that's where the electric field is strongest. Whereas in this case, it selects its own natural length scale. Now, the distances look similar, but they're not. This is just the way we set it up. Okay, so you can actually, these don't have to be equispaced and so forth. You can even generate, you can print words if you want with these things. Okay, so this is what happened without, this is what happens without any flow, right? Everything was the layer I had before, just sitting happily on the substrate. Now, what happens if I add the background flow? Well, here's an experiment that was done at NJIT while I was there with Nadine Aubrey and another colleague, Peter Petropoulos, and the postdoc. And what you see here is a T-junction. So it's a channel. So think of this as a microchannel. So what we're going to do is flow two fluids, one from that side, another one from that side. They're immiscible. They're oil-based immiscible liquids. So they will form an interface. There will be two different regions. And then this device is etched with electrodes of length 38 millimeters. The total length is about 7 centimeters, and the height is about 1.5 millimeters. So the parameters are chosen so that without any electric fields, the flows are stable. Okay, so what we want to see is what happens when we switch on electric fields. Can I force this flow out of its stable equilibrium? So here are the two fluids, they're corn oil and glycerine. So rather than, I'll just tell you what the outcome is, because I may not play the whole movie, and then we'll show the movie. So what happens is that this forcing of these electric field effects cause an instability, a breakup of the interface into plugs of fluid, as we will see. So there will be a plug of one fluid within the other, and then they get pushed outside of the electrode region, downstream, where they form bubbles, so droplets. So this is a way, this is a technique of separating, if you like, the two flows into a monochromatic distribution of droplets, whose size goes down as the voltage goes up, as the electric field goes up. So let's see the movie. I think that's much more instructive than me just talking. So it's a long movie, so let me play it. Okay, so this just gives the geometry. So now the flow is on now, right? So it's a two-phase Poiseuille flow. So the flow is on, the electric field is switched off. There's the interface, flat and happy to go along. Okay, now the electric field is turned on, and we see a linear instability to begin with. Eventually it becomes high amplitude, non-linear, and you will see it will start wagging and oscillating, and at some point it's going to hit the bottom as well. This was very difficult to get the camera at the right place, but once this settles down, I will put the mouse, if you can see my mouse, where the impact point is. Okay, so there's the impact point. So let's think about this. So impact there, and then another impact. So that generates the separation. Okay, so that creates now a slug that's sliding along on the bottom electrode, and then if it goes outside, okay, a bit further down, there's the slug still underneath the electrode. So that's the other fluid. Here's fluid 2, fluid 1, and it happily just travels along. And then eventually, when it goes further down outside of the region where the electric field is acting, it relaxes into these Brotherton droplets, bubbles. They're known as Brotherton bubbles. Okay, because these are high surface tension. So at different voltages, you just get different sizes coming down. So let me not play the whole movie. You get the idea. Okay, so we made an attempt at simulating this with finite volume front tracking methods, interface tracking methods. And this was done in a general case. We'll go through the electrohydrodynamics equations in a minute. But the idea was to try and reproduce this. So we did this in a channel with Stefan Malman at NJIT in 2011. I think this was published. And we do indeed can get our simulation to hit the bottom wall. So this event would be this first touching event that the experiment was showing. Of course, we couldn't go further. In the Navier-Stokes equations, the pressure just underneath that point blows up, right? So you need to do some surgery and then change the type of code. So we weren't that sophisticated to do this, but we saw the onset at least. Okay, so a quick review now of the equations of motion for electrostatics. Okay, so what do I mean by that? If I start from the Maxwell's equations, the induced magnetic fields in these types of voltages we're using are small. So, so there are no magnetic fields. So the equations that govern the electrodynamics are Gauss's law, right? So that's Gauss's law. This is Faraday's law. Then we have charge conservation. So all these things are valid in the bulk of the flow, right? So E is the electric field, Q is the charge density per unit volume, J is the current, sigma is the conductivity, and U, of course, is the velocity. So what do we have? Well, we've got conservation of charge. So this is comes directly from Ohm's law, where the current is given here. And we're going to make a small simplification. Well, it goes a long way, in fact. For incompressible flows and constant conductivity, I can rewrite this equation, the charge conservation equation, into this form. And now if I look at this, well, immediately I can see that if I go along characteristics, then this is an ODE for Q, dq dt is minus sigma over epsilon Q. And it turns out that for most systems that we use, and definitely the one, the experiment I showed before, sigma over epsilon is very large, okay, or epsilon over sigma is very small. And this is called the fast relaxation time limit. Now, what does this mean physically? Well, mathematically, the charges will go to zero. So physically, what this says is that very quickly, any charges that are in the liquid will go onto the interface or the walls, right? So they'll want to leave the bulk. And hence, Q is zero everywhere in the liquid. Then we need to we need to see what equations we must solve for the voltages. So what we have now is the Kortweg-Helmholtz force density. So this is the force density in the bulk of the liquid due to an electric field. And again, you can see that this involves the gradient of the permittivity. So again, so I can rewrite this as the divergence of a force, and this becomes very useful because this tensor here is what's going to appear in the force balances at the interface, in the tangential and normal stress balances. Now, if epsilon, the permittivity, is constant in two different fluids, but different, two different constants in the two different fluids, of course, the gradient of epsilon is singular, right? It's like a delta function. So all the action is going to happen at the interface. So all the forces will be at the interface. So away from the interface, what we have is from Faraday's law, I can define a potential. And then from Gauss's law, since we showed Q is zero, and epsilon is constant away from interfaces, then all this complicated looking system of equations reduced to the Laplacian of a scalar equals zero. So mathematicians are in their comfort zone once again, right? So we just have Laplace equations. So what about the hydrodynamics? Well, similar types of things. I think everyone's seen this. I just rewrote it in terms of the divergence of a tensor that's given here, right? So this is the usual Cauchy tensor of the Navier-Stokes equations. P is the pressure, mu is the viscosity. So what we have is the two sets of equations do not couple, right? I have Laplacian V is zero. I have something that just involves U and P for the Navier-Stokes. They don't couple, but all the coupling happens at the interface. And that's where the nonlinearity, well, even for cases where it's slow flow, where the nonlinearity will come in. So what are the interfacial conditions? So this is a general situation where a two-dimensional surface, where I can write it as the graph of a function. Okay, so we'll keep it that way. Big H of x, y, and t is the height of this interface. So if I define a position vector on the interface and the usual jump notation for quantities across the interface, then I have to really think of forces normal to a point at the surface and in a plane, a tangent plane at this point through which the normal, whose normal is n. Okay, so we need to consider the total stress, which is mf plus me, and these are the full boundary conditions. Okay, what do I want to say here? I don't want to say too much, besides the fact that the coupling, if you have a charge at the interface, right? If there's a charge at the interface, then it can generate tangential stresses. So in fact, you can get situations where you can also cause flow simply by generating tangential stresses at the interface. And this is kind of related to the electrokinetic effects. So what are these? These are tangential stresses in the T1 and T2 directions. This is continuity of velocities. This is normal stress balances. So this is where surface tension comes in. And this is a kinematic condition. And this is just the curvature. Now for the electrostatic conditions, what do we have? Well, we've got the tangential component of the electric field is continuous. So that implies that the voltage potential is continuous across the interface. Then I have a Gauss law, as we saw before. Now again, if Q is 0, then that will just give me a 0. So there are two different limits that I will consider next. So this is the most general situation that goes by the name of leaky dielectric model, which was coined by Melcher and Taylor in 1960. Okay, so here's two particular cases that we will take. So to simplify things a bit, even though we've done a lot of work with the leaky dielectrics as well. So there are two situations. One is when the liquids are perfect dielectrics. In other words, they're non-conducting. Okay, so that means there are no charges in the bulk. If there are charges at the interface, I can ground them and get rid of them. So without loss of generality, I could have no charges everywhere. So that means I have to solve Laplace's equation, harmonic fields in the different regions, and then at the interface, I have these two conditions. Okay, one is a jump in the potential, the other one is almost a jump in the normal derivative, but it's got the epsilon there, which is also different in the two regions. Imposing voltages at infinity or walls and so forth closes this problem. A perfectly conducting fluid situation would be when one fluid is a perfect conductor. In other words, if I electrify, it will take on that voltage everywhere. And therefore, it has, it has a Dirichlet condition. It will impose a Dirichlet condition for the upper region where an electric field will act. So we'll take that to be a perfect dielectric, say. So this now decouples fluid mechanics with electric fields in two different regions. So this has a very nice mathematical structure in that it involves to solve the hydrodynamic problem, you need to go from the Dirichlet to the Neumann map to feed into the hydrodynamics equation, as we will see in a second. So some simple problems. I'm probably really slow. I'll speed up. Here's some simple observations. let's just take two fluids, fluid 1, fluid 2. One could be heavier than the other, okay, for the moment. And I'm going to do two different things. I'm going to impose either a vertical electric field, okay, in other words, put an electrode there, and have a potential difference across them. And of course, mathematically, I can think of sending the electrodes to infinity in such a way that the voltage will grow linearly with vertical distance, a bit like a shear flow, but for a voltage. So, so this will be a vertical electric field, and this one will be a horizontal electric field. Okay, so so in this case, the field far away will look like y, if y is that way, and the field very far away here will look like x. Okay, so one vertical, one horizontal. And let's do linear stability theory based on those equations we had before. Disturbances of the form e to the ikx minus omega t. If omega is complex, I can then get growth, right? So it turns out that I'm just doing ideal fluids now, right? Inviscid, and so everything's nice. So I end up with a dispersion relation that essentially gives me omega squared. So omega is this quantity here. So we can see if omega squared is positive, then this is dispersive, right? So I don't get any growth. Whereas if omega squared is negative, this will give me positive eigenvalues and therefore instabilities. So here's what happens. Vertical field, this is a dispersion relation. Horizontal field, this is a dispersion relation. Almost the same, modulo some things, but the main difference is this is plus, this is minus. Okay, so what this is saying is that, so let me say a couple of more things. This is Rayleigh-Taylor instability. Okay, this says that if the heavy fluid is on top, okay, and I think my row, this is row 1, this is row 2, right? So, so row 2, if the heavy fluid is on top, this is negative and therefore unstable, so, right? So a heavy fluid will fall down. Surface tension is here. It's always dispersively stabilizing for ideal flows. For short waves, it will dispersively stabilize short waves. But now the electric field will be destabilizing if it's vertical, and it will be stabilizing if it's horizontal. That's what this is telling me, right? Because it's positive in this case. So in the experiment I showed, the NJIT experiment, it was vertical, right? So I'll show you. In the experiment I showed before, it was vertical. So it was destabilizing, and that's what caused all that breakup of the interface into droplets. Now, what happens if the field is horizontal? Well, we could expect that even in situations where row 2 is bigger than row 1, in other words, heavy fluid over light fluid and it wants to fall down, if I make the field big enough, I should be able to stabilize it. Okay, so the question is, how does this manifest itself computationally? So again, here's where Radu's magic came in. This is a paper we published in 2014. I think this might have been for Radu's PhD, even, I can't remember. And so let me show you a DNS simulation where I will increase the electric field and just see what happens. So a heavy fluid, this is a heavy fluid lying on top of a light fluid. So let's just see the simulation. The field is increasing as I move to the right, from left to right. Okay, so we can see without any field, this is the leftmost figure. It's heavy, so it's going to fall down, and it will fall down and form these mushroom type structures that we saw before, and it keeps So this will win because it's heavier. Sorry, it's got the zero field. As the field increases, the instability decreases, and we can see that with a field of this value, I think 4 in our dimensionless units, whatever that means, is completely stable. Okay, so it just stabilizes completely. So this is a kind of very interesting, a very interesting open problem is that of vortex sheets, and that's something we've started looking at recently. If you take vortex sheets and you so a vortex sheet would sit where the instability would also be k squared. Okay, if I had the vortex sheet, omega squared would be k squared because it's a short wave instability for all wave numbers. It's k for all wave numbers. So the question is, what happens if you try and electrify that? How would it affect the singularities and so forth? So that's something we're looking at. We're not there yet. Okay, so let me now move on to some nonlinear theories. Just give you an idea of what we can do. You saw what we can do with simulations. Now let's look at nonlinear theories. And in particular, I'm going to try and do some long wave asymptotic theories where the wavelengths will be long compared to the vertical distance of the channel, let's say. Okay, so there are two types of these theories. There's a theory where the wavelength is long and also the interface is as large as the channel thickness. So it can go and hit the wall, like the topography simulations I showed earlier. But there's also situations where one of the fluids is thin relative to the other one, okay? Or this could be a thin falling liquid film with an electric field generated by an electrode that's spaced far enough apart, right? So in this case, so here's the upshot of this. In this case, you get local type equations, nonlinear local equations. In this case, you can get non-local pseudo-differential type equations. So we've done both, and I'll show you bits of both if I speed up. Okay, so here's a warm-up problem. So this is just to set the stage of the types of things we can do with these things. So let's think of two inviscid perfect dielectric fluids. This is, by the way, this is work with Henry Broadley, who was an undergraduate. He did this as part of his undergraduate thesis project, and now we're continuing it while he's doing his PhD at Manchester. So this is a channel, two fluids, inviscid fluids, and there could be a flow and so forth, and I'm electrifying them vertically, right? So the voltage here is 0, the voltage here is V0, some constant. Different densities, different potentials, voltage, as well as velocity potentials, because these are inviscid flows. So again, what do we have to do now? Well, we have to solve two Laplace equations in each region and match them across non-linearly, this interface. So this is the simplest possible situation you could encounter. So for long waves, right, if d by dx is small, epsilon, let's say, so my d by dx will be epsilon, d by dy is order 1. So what do I do? Well, I can do asymptotic expansions. It turns out they're in powers of epsilon squared. And I can expand everything in sight in terms of epsilon squared. Then I've got boundary conditions at the walls at plus or minus 1, no penetration for the flow, right? 0 vertical velocity. And also it's 1 at the top wall. I've non-dimensionalized, the voltage potential is 1 or 0 at the bottom wall. Okay, so what do we have? Well, we've got two kinematic conditions because the flow is inviscid. So there are now two kinematic conditions, one from above, one from below. there is a Bernoulli equation. There's an equation, there's an integral of the equations, of the Euler equations, that gives us a Bernoulli equation. Then we have a Gauss law. These are perfect dielectric fluids, and voltage continuity. So these are the boundary conditions. So again, as I said, this is very clean because it's the simplest case we can do, just to give us the mathematical structures. So these are second order, 4 second order equations, therefore 8 constants. The interface is also an unknown. I don't know the interface. It has to be solved as part of the solution. So I have 9 equations, 9 unknowns. So in principle, I should be able to solve this. Well, it kind of takes a bit of fiddling around and identifying the right things. But once you do that, you can get this down to a system of 2 coupled equations. One for S, which is the shape of the interface, the other one for this capital delta, which involves the jump in horizontal velocities, but scaled by this quantity where alpha is the Atwood ratio. The Atwood ratio is going to be either 0 when the densities are equal, or 1 when the upper layer has 0 density, when it's passive. I'm not telling you what Q1 to Q4 are. They're rational polynomials that we know, and this is the surface tension term. Okay, so without this term, this system is at best hyperbolic. Okay, in fact, I can write it in conservative form, but that's not quite true. That's not quite the story. It's actually not hyperbolic. It's quite interesting because it has these hyperbolic to elliptic transition regions. So depending on what the size of the different of the S and the delta is, it can transition, as we will see. So in any case, let's go back. So here's a system I can now play with. And the first thing we did is look for solitary waves for this. Okay, if you do anything with ortho waves, the first thing you do is you look for some traveling waves, and then try and see if you can get solitary waves. And we did that. And amazingly, you can do 2 integrations and get this down to a phase plane. So you can actually integrate that exactly to this form where P3 is some 3rd degree polynomial that we know. It depends on all the parameters. And now what's interesting about this, it's got this term 1 over 1 minus s squared. Now don't forget that I'm in a channel, and s is between -1 and 1, right? So this is where s lives. So s tends to 1 or -1. This thing will go to 0, right? This will go to 0, and therefore this will either go to +infinity or -infinity, right? So you can see that, first of all, I've got solitary waves. This is built in. The solitary waves are because of this, right? I've built it in. So everything depends on the geometry of this, on the roots, essentially, of this polynomial. So let me give you some examples. Let me give you an example of that function, and then this is the phase plane of that function s dx squared, right? And like we said before, it all depends on the roots of the polynomial. So the polynomial P3 happened, or was constructed. We looked for parameters where there were 2 roots, 2 real roots between -1 and 1. So here's one, here's another, and then because of that 1 minus s squared on the bottom, this goes to -infinity. So the only place I can get admissible solutions is here. And this tells me that there are 2 solitary waves, one wave of elevation that will come from this, the other one a solitary wave of depression that comes out of that. Now, if I take this, the positive values, take the square root and plot the phase plane, this is what the phase plane looks like. So this is the maximum, right? So I start at the maximum value of S, where ds is 0. So that's the maximum. It's symmetric, of course. And then I go around, and as I go into the origin, I go to plus infinity. And then below, I go to minus infinity. Okay, so there's actually exponential decay. So here's what these waves look like. So this is the depression solitary wave. This is the elevation solitary wave. Now, the color coding here, the bits that are coded blue, mean that the eigenvalues of this matrix, okay, so this is this matrix is involves rational polynomials of S and delta, so I can locally evaluate this matrix and find its eigenvalues as a sweep through X. So for part of the interval, it will give me hyperbolic real eigenvalues, and part of the interval, it will give me complex eigenvalues. So, and this is completely due to the electric field. So, so this begs very interesting questions of what's the zero dispersion limit of things like this. And well, clearly they're ill-posed in time because they suffer from shortwave instabilities. Okay, so of course it would be interesting to connect this to the Euler equations. And what I want to say here is that the hyperbolic to elliptic type behavior for the flux functions seems to be fairly generic in what we're doing, at least. And it doesn't have to do with electric fields only or in viscid flows. In fact, there's a situation where we found it for linearly stable systems even at 0 Reynolds numbers. So this would be, so if you think of a channel flow now with 1, 2, 3 fluids and 0 Reynolds number, very, very high viscosity, slow viscous flows, again, I get a coupled system of PDEs because of the interfaces, and that will give me, I'm not going to show the movie, that will give me, again, hyperbolic to elliptic transitions, and that's what makes the flow unstable. Otherwise, it would be completely stable. So linearly stable, it can be linearly stable, but non-linearly unstable exactly because of these transitions. Okay, so let me continue with viscous flows and see if I can get through it. So now we go to viscous flows, and what I show here, what I'm going to show here is 3-dimensional falling film flows. So this, you just think of a pane of glass with a tiny film of fluid that's falling down under gravity. So the thickness of the fluid is about sub-millimeter at most. And what happens, again, experience shows that as the flow moves down, it goes unstable to kind of 2-dimensional waves to begin with, or 1-dimensional fronts, and then eventually it goes to these span-wise instabilities, 3-dimensional fronts. So what I want to do is see what happens if I have electric fields in all of this, where such flows may be stable. So I'm going to do two things. I'm going to take these types of flows now, consider situations where they're stable. So you can imagine if the angle is very shallow, then they will be stable, and indeed that's the case. And then by putting a vertical electric field, I can make them become unstable, cause the interface to oscillate and enhance heat transfer and so forth. That's the first problem. The second problem will be to invert this so that the film is hanging down, so it wants to drip. And then I want to use an electric field to stop it from dripping, to see if I can control it. And also suction. Okay, so we'll see this. So let me go through this quickly so that I can get to the good stuff. So initially, let's take the film driven by gravity and an electric field. Okay, so again, I'm going to use a perfect conductor fluid. So I'm going to, again, only look at fluid dynamics in one region, only, and electrostatics only in another region. Okay, this is viscous now, so I get a half parabolic profile. I just get a kind of a half Poisson profile. And this is just to say what the parameters are: Reynolds number, Weber number, and a capillary number. Okay, so this is, there exists an exact solution of the Navier-Stokes, which is uniform. So the interface is now given as a function of two variables, x, y, and time. And again, this now is in case two of these two canonical long wave things I showed. Okay, so now one region is thin, right? It's got, it's going to be long, right? Very long. So we'll take, so you either make it thin and order 1 or very long and thickness 1, right? It doesn't matter. It's just the scaling between them. So x and y, which is the distance in the coordinates of the plate, the coordinates in the plate, x and y are of order 1 over delta, and the thickness is order 1. So it's thin compared to them. So these are the expansions for the liquid region, okay? And then we'll keep surface tension and electric stresses. Now, in the outside region, where now the field, the boundary conditions are at infinity. So now this has to be a square domain. So if I look for a perturbation about this uniform field at infinity, then I end up with a Laplace problem with a Dirichlet boundary condition, okay, which involves the interface, which of course I don't know. I need to find it. But in order to find it, I need to get the Neumann, this Dirichlet, I need to solve this problem, get the Dirichlet to Neumann map, get the derivative, the normal derivative that will then feed back into the fluid problem. Okay, so these are the details. So if you do all that, and you can solve this with Fourier transforms, of course. So this is the Ries transform in 2D. So if you do all that and put everything together, you end up with a nonlinear partial differential equation shown here. So let me point out a few things here. So if you look at all these terms, so this is two-dimensional, of course, but if you look at all these terms, this one and all of these have a delta in them, and delta is supposed to be small, right? So if I put delta equals 0, I just get a hyperbolic type equation, and I will not get bounded spatial derivatives. So what I want to do is, instead of working with this equation, we can go further and get rid of the delta by doing a weakly nonlinear expansion. Okay, so in other words, I know that H is 1 is an exact solution of this. Okay, so I make it 1 plus a little bit, and then pick the little bit to keep nonlinearity. And how does that go? Well, if you do that, if you make this transformation in this nonlinear degenerate PDE, right, then I end up with this. So putting this in here, this is what I get. And then what do I do? Well, let me go back. So we can see that with a Galilean transformation, I can get rid of this term, right? I can get rid of this term and introduce another slow time scale. And then every term in the equation is delta squared. And I have nonlinearity as well. Okay, so the desired equation will come in at delta squared. Okay, for those who are very familiar with this stuff, if you make this kind of a little bit smaller even, and include delta cubed terms, you can get dispersion coming in the form of the KdV equation. So you can get a mixed Kuromoto-Sivashinsky KdV equation. So finally, this is the equation. Okay, so what do we have? Well, it's a scalar, that's the interface, function of x and y and t. here's my Berger's nonlinearity because it flows in the x direction. And then I have this term that comes from inertia. It tells me that if inertia is big enough, if the Reynolds number is big enough, this is positive, therefore it's negative diffusion, therefore it's unstable. This is a stabilizing term because of the, it's Rayleigh-Taylor stable. That's why if I turn it upside down, then this will be positive too. This is the electric field term. Okay, so it's the Laplacian of that non-local term. And then this is surface tension. So this is the PDE. So what we can do is solve this on kind of square domains, doubly periodic square domains. If d dy is 0, you get a 1D version, and we did a lot of work on that. And also, you can also prove the existence of inertial manifolds, actually, for this equation, even with this non-local term, right, in 1D. Okay, so a linear dispersion relation, just to get an idea of what's going on. A linear dispersion relation is shown here. So as I said before, this is the inertia, the K1 squared. Gravity is always going to be stabilizing. The electric field is always destabilizing, and surface tension will kill large wave numbers. So that's very important and necessary. Now, as I decrease these parameters, okay, these parameters, if you look at them, it's 2 pi over L1, 2 pi over L2. So as I make the size of my system bigger, these parameters go to 0. So it's a little bit like a zero diffusion limit, if you like, where that term would get smaller and smaller. Okay, so there's, if I go back, let me go back here. If you look at, right, if you look at this equation, oh, this is the linear equation. I don't want to look at that. If you look at this equation, the nonlinear equation, any kind of interaction of modes will get mixed up, right? So this term will mix up modes, long wave, short wave, and everything. So there's a nonlinear interaction, and it will distribute the energy over all these modes. However, there's no such mechanism in the y direction. Okay, there's no eta y term. So any growing modes, span-wise modes, have no hope of being nonlinearly saturated. Okay, so this is one issue with this equation. And that happens if gamma is bigger than 2. Okay, so as long as gamma is less than 2, then we're okay. So let me see if what I can do quickly. I'll show you some simulations and then I'll stop. So what I want to do now is set gamma equal 2 and then vary my parameters L. I'm taking square domains now, right? So it doesn't matter. Square domains L by L, and then I'm going to vary beta. If beta is less than 1, then I'm in the stable regime, right? Inertia is not, Reynolds number is not big enough to give me destabilization. So what's shown here, these are just linear properties of the equation. The color coding just says the number of modes that are unstable. Okay, so I start off, so for example, beta is 0.01. As I go through, I get 1 unstable mode, then none, 1, and then as I go down, the length gets bigger and bigger, mu goes to 0, I get more and more modes. And this is the line where we live in this domain L by L. Okay, so that's the line. So I'll show you simulations as I go along those lines. So here's simulation for beta is 0.01. This is work that Ruben did. This is in the JFM a few years ago, 2 years maybe, I can't remember. So So this is a case with L equals 13. Nu is 0.48, so we're kind of here in this region. So we're in the yellow region. So there's one unstable mode. Okay, so let's see what this looks like. So what I'm showing here is the phase plane of the L2 norm. So as I go around the phase plane of the L2 norm, so we see that the solution is one-dimensional. It's these fronts, right? These fronts that we saw in the experiment in the very beginning, but then there's a three-dimensional departure and goes back to this almost one-dimensional flow again. Okay, so and then it just carries on forever, right? So it's a homoclinic burst, right? With that point, the homoclinic point. Now, what about a slightly different situation? So now this is 0.33, so we're kind of down here somewhere. Okay, so what happens here? This is a quasi-periodic solution in time. And again, this is the phase plane. And then it aligns when it gets stuck in this region, right? In this kind of homoclinic point, it aligns, and this is very interesting, right? It gives us structures that align with the direction of the flow. So these are like rivulets, right? That go down the flow. And then there's a departure. It gives me these waves. And then it just keeps repeating, okay, in a quasi-periodic manner. So here's a situation when I make beta a bit bigger. So now inertia is a little bit bigger, but it's still below its linearly stable case. So without an electric field, everything is stable. So the value now is 0.873. So I don't know, it's there somewhere. So it looks like there's two unstable modes, and again, these are very interesting solutions. So let's look at them. This is an exactly time periodic solution. Okay, so what it does, it almost gives an almost front solution, but then it has a departure. So you can see that all these are related, right? So it departs from this almost 2D front to give three-dimensional oscillations. And then this one is a slightly smaller value, bigger L, right? About twice the value. And now this is fully three-dimensional, and it just gives a quasi-periodic oscillation in time. Okay, so this is what happens with fixed values of the electric field. Now let's do something else. Okay, let's do something else. Now I'm going to fix beta equals 2, and so what I'm going to do is start with no electric field and start increasing the electric field. Okay, and so let's see what we can do. So this is a way of controlling the flow, if you like, with the electric field. So without an electric field, what we get is that it will be this two-dimensional Kuromatsu-Washinsky equation. And if you let this go for a long time, I shouldn't do that. If you let this go for a long time, you find that the oscillation is quasi 1D and chaotic. Okay, but you really have to integrate to hundreds, thousands of time units to see it. Now I've switched on the field, okay, and I made it gamma. Gamma is 1. Okay, I've switched it on, and I get a slightly different situation where I get this front, but I'm also introducing span-wise oscillations. Okay, so I'm making the flow a little bit worse. And now I'm going to ramp it up even further. Okay, so now gamma is 2, and now you can see that I've made it completely chaotic, right? So this 2D cellular scaffold is completely lost, and the flow is chaotic. We can identify chaos in these cases. We've got various ways of doing it. Okay, And Elena, tell me when to stop.
Let me see. Yeah, I mean, we have like five more minutes.
Okay. So let me show that very quickly something then. So what I showed there was with vertical electric fields, I could destabilize things. Now I want to put a liquid on the underside of the plate with gravity acting, and of course we know that it will drip, right? So, but now I want to use a horizontal electric field to stabilize it. We can also do it with blowing and suction, okay? But I don't have time to do this, so let me skip this, and I'll. By the way, there's a paper. If you're interested, there's a paper on this. I have references at the end as well. So let me skip this and go to this dripping problem that's motivated by experiments. So this is an experiment by this group, by Galaire's group, where they put the liquid on top of a plate, and then they swung it around, and you can watch what happens from the top, and you get this dripping. So you can see, of course, it's all three-dimensional, right? It's drops. Our theory is going to be 2D. So what we want to do is introduce a parallel electric field. So this is our setup. So the setup is this. Here's the liquid, and I have an electric field. In fact, now we're including the solid region as a dielectric, because usually it's plastic and it is a dielectric. So in doing this, now I have one Laplace equation there, Navier-Stokes there, and another Laplace equation there for the field. Okay, now what happens experimentally, they made a conjecture saying that when they see a transition from convective to absolute instability, then that's a kind of the event of dripping. Okay, and we can analyze all these flows for absolute convective instabilities using the Briggs-Burrs criterion or some other method that I did with Thanasis a few years ago. Now, this is just a picture to show what absolute and convective instability really is, and let me just do it in two phrases. This is convective instability. It says that if I'm an observer and I sit there, so this is the xt plane, right? I'm an observer and I sit there and watch what's happening. As time goes along, right, I don't see anything, then I will see, here's all the stuff, I'll see the wave, and then as time goes on, the wave goes past, it's gone, right? So that's convective instability. Absolute instability, it doesn't matter where I am as an observer, doesn't matter where I am, if I wait long enough, the flow will be unstable everywhere. Okay, so again, this is done. This is done by just looking at the dispersion relation and looking for saddle points, pinch points in the dispersion relation. Here's a pinch point. Let me point it out. Actually, here it shows a bit better. Let me point it out here. If you look at this case, E equals 40. It's a value of an electric field. So these are the roots of the dispersion relation in the complex plane, and you can see there are two branches. So if this branch connects 0 to infinity, it means I can deform and get everything into a convective instability. As I decrease E, right, you can see here, and now between 20 and 0, there's a pinch event, right? So there will be a singularity there at some value of E between 0 and 20, and then I cannot connect infinity to 0, and this is where I get absolute instability. Okay, so this is just to show some simulations. This is work again with Radu and Ruben. If you have an absolute instability, then you can see growth of these wave packets in both directions. It's exactly this, right? Whereas if you don't, you won't see growth. Everything will be in a wedge, right? The front and back of the wave packet will be a wedge. So what I want to show you, and then I'll stop, is a movie where we will take three situations. Two of them, I think, where they drip, so they're in the absolute kind of regime, absolute instability regime, and one where the field is big enough and it doesn't drip. So let's see if we can do that. Okay, and this is kind of shown flat, but you should think of it as inclined, right? So you can see the dripping events. So these are the amazing simulations that Radu can do. So you can see the dripping, and the lower one, right? This one has a large enough electric field and it's completely stabilized it, right? So we don't get any dripping effects at all. Okay, by the way, we can also do this with blowing and suction. Okay, but that's for a different day. Okay, so some conclusions. I still think there's a lot to do, especially kind of mathematical modeling. I think there's a lot of things there to do still. Passive and active control based on realistic mathematical modeling. I think that's a very good area as well. Inverse problems, again, would be very interesting for these types of flows. They've been used for a large scale things like aerodynamics and so forth. Rigorous analysis of the equations, especially global existence of these nonlinear degenerate equations, definitely not known, and three-dimensional phenomena. And then since you're recording, let me just go through and just show these. 1, 2, and then people can just go back and look at them. And I'll stop there. Sorry to go over, Elena.
No problem, no problem. Thank you very much. Let me stop recording now.
But of course, happy to